Hello, today I'm going to be showing two different neural networks I made that both are able to drive a car around a track. The first one I'm going to be showing is a neural network that uses imitation learning, and the second one is going to be one that uses reinforcement learning. So this is the first neural network, which is imitation learning. Unfortunately, I didn't document much of the process, so I only have a video of the final result. But how it works is it takes in data of how an actual human plays and then tries to imitate that. But it can then also use that data to be able to drive on other tracks. To collect data of how an actual human drives, I drove around the track and I made the program collect data about how I was driving around the track every few milliseconds. So each instance of this data had a state and an action. For the state, I had raycasts coming out of the car. Raycasts will tell you the distance to a wall in a certain direction. I didn't have any raycasts coming out the back of the car because that information wasn't important for driving. I just had around 8 or 9 raycasts coming out the front of the car in different directions, which allowed the car to know the distance to walls in front of it, to the left of it, and so on. And the action is just whether I decided to turn left or right. In the imitation learning example, the driving model isn't very advanced, so the car just drives at a constant speed and the only actions are either turning left or right. So I collected around 3 minutes of data of just me driving around the track, and I made sure not to crash at all so that the neural network wouldn't learn to crash. The neural network itself is pretty simple. It's just 3 linear layers, and then to train it on the data, I just use MSE loss because it's pretty simple. It's just either choosing one action or the other. The negative of imitation learning is that the neural network's only going to ever learn to drive as well as I am able to. In reinforcement learning, the neural network's able to keep training until it optimizes the driving perfectly, where it will have the fastest possible lap time. But this also has positives. Unlike reinforcement learning, which can take a few hours or even days, this trains really quickly. It can train in about 30 seconds, and the results are pretty okay. It also works on other tracks as well. So I'm able to just draw another track, and it, again, won't be perfect, but it's still able to drive around that track. Before I started making the reinforcement learning neural network, I first improved the driving model. So now the car is a lot faster, and also you actually need to brake on turns. And in general, the driving feels a lot more realistic, and it'll be a lot more challenging for the neural network to learn how to drive around the track without crashing into walls. So in order to make reinforcement learning, I have to be able to collect data about the state of the car at a certain instance. So to do this, I again made raycasts. So you can see all of the raycasts drawn out of the car. And I also am gathering more than just the distance of the raycast. I'm also gathering whether the raycast is hitting the outer wall or the inner wall. So you can see that the darker blue raycasts are the ones hitting the inner wall, and the lighter blue ones are hitting the outer wall. And the reason I'm doing this is because using that information, I can know whether the car is going in the right direction or the wrong direction because if the very left raycast is hitting the inner wall and the light blue raycast or the very right raycast is hitting the outer wall, I know it's going in the right direction. If it's the opposite, I know it's going in the wrong direction. Next, I added gates. Gates would allow the neural network to train a lot better because I could track the car's progress along the track and reward the neural network for going farther along the track. And this will help the neural network know that moving forward is beneficial to it. And also, I'm able to track laps, which will later, when I'm really optimizing the lap time, allow me to track lap times and all of that. As you can see, when the car touches a gate, it turns green. I also made sure that the car's not getting a reward whenever it's just touching a gate. It only gets a reward at the instance it touches a gate, and then that gate turns green and that gate will no longer count for a reward. Otherwise, the car would probably just end up going in circles, continuing to use that gate for a reward. So after I have all of this set up, I begin the training of the neural network. For calculating the loss, I used a policy gradient, which collects episodes of data. An episode is, for example, 5 seconds of the car driving, and it's an array of rewards for each instance of the car driving. The rewards are calculated using the state. So, for example, like I mentioned earlier, um, there's a positive reward for moving in the right direction. I also have it's the neural network's rewarded for having a speed higher than a specified amount to make sure that it knows that moving is good. It also has rewards for example, at the start of training, I made it so that it gets a reward for braking if the distance to the wall in front of it's less than a certain distance, which helps it learn at least like the basics of driving to make sure it doesn't just continue crashing into a wall. There's also rewards for hitting a gate or also finishing a lap, and also finishing a lap with a faster lap time than the previous one. And all these rewards get calculated into one, they get summed up, and each instance has a reward. And then what the policy gradient does, it'll go back through this episode and change the weights in the neural network, which, by the way, is the same neural network I used in the imitation learning. It's also 3 layers of just linear layers. And also, when it's going back through that array and changing the weights, it weights the events or the instances that happen closer to the end of the episode more highly. Because, for example, if it crashed and the episode ended, we want to mostly focus on the data where it crashed, because we don't want to have negative rewards for the stuff where it's driving correctly straight on a turn or something. We only want to have a big negative reward for the events that led the car to crash. The video you're seeing now is before I implemented a reward for braking, and also before I implemented random positioning. Because of that, you can see that, first of all, it's just speeding straight into the walls and it's not really braking. And also it's still not driving as well as I would like it to be. It's sort of plateaued, the progress plateaued. And to fix this, I added the random positioning, which means that after each episode, or after each time it dies or crashes into a wall, the position in which the car will respawn is random, and it just chooses a random gate and calculates the center of that gate and also the angle of that gate, and just drops off the car in a random position on the track. And also I added a reward for braking if the distance to the wall in front of it is less than some specified amount. So here you can see this is the start of the training, and you can see that it's not really moving anywhere, it's just sort of wiggling. And also here you can see the implementation of the random positioning. So at the end of every episode, it respawns to a random position on the track. This is a bit further into the training process. You can see that it's learned to move forward and also turn in the general direction of the track, but it's still not perfect. It still needs to learn how to brake more accurately and also turn the right amount. This is even further into the training process, and you can see that it's able to drive pretty large portions of the track, but it's still not at the point where it can drive a full lap, or well, it sometimes can, but it's not consistent, and it's still learning a bit about how not to crash. So far, this is the most I've trained it, so this is the best variant I have so far. It can consistently drive full laps without crashing. It's not as fast as I would want it to be yet, so it's not taking like the best racing line and all of that, but that'll come with more training. But so far, this is the best variant I have. As you can see, it's definitely able to drive the entire lap. There are moments where it gets really close to walls and it's not really being as fast as it should be, but overall, this I'd say sort of matches with the imitation learning, and I can definitely take this farther with more training. Also, this is using a more simple reinforcement learning algorithm. If I wanted to, I could implement actor critic, which would make the training a lot faster and probably I would have better results. But so far, I think that with more training, I'll get this car to drive pretty well along the track and get a really good racing line. So I hope you enjoyed this video. If you're interested in looking at any of the code or trying to test these programs for yourself, I will link both the imitation learning GitHub repository and the reinforcement learning GitHub repository in the description. And yeah, thank you for watching.